Hi guys. So finally, we're going to get to the topic that I actually find most interesting in number theory, an application of number theory, cryptography. Um, it's arguable, but I think a good case can be made for the idea that cryptography, the actually I should mention there's this word cryptography. The etymology of it is crypt, which sounds like it has to do with graves, but it really just means hidden in Greek, and graphy, which means writing. So that literally means hidden writing. There is another word that sometimes is confused for cryptography, cryptology. Um, People tend to use that word in Britain more than in the US, but basically cryptography is the idea of creating codes that allow you to send secret messages. Cryptology, in most usage anyway, cryptology is the study of how to analyze codes and to break them. So this is, you can think of this as making codes and breaking codes, more or less. Anyway, I was going to say an argument can be made that World War II ended the way it did because of cryptology. In particular, in Britain, at a place called Bletchley Park, they put together a team of people and actually built some of the world's first, usable computing equipment in order to break a crypto system that the Germans had created. And they were successful, and they were able to, usually within a day of a new code being introduced. So you see, the Germans knew that it would be possible to break their system, so they changed the code every day. That doesn't mean they literally had to change everything, but the settings on the machines that did the encoding would be changed on a regular schedule. And the folks at Bletchley Park kept up with it. They kept, each time a new setting was done, they would get to work on. There's a whole system of radio listening that was going on. The people at that time used Morse code, right? They didn't actually have voice radios like we're used to today. So they were hitting dots and dashes on a radio transmitter to send encoded information. And anybody could listen to the radio and hear these Morse code messages. Germans didn't care because it was encoded and it was supposedly, hidden writing. But that didn't last. Once they got a fair sampling of messages that had been encoded with the new cipher, the cryptologists at Bletchley Park got to work and they would break the codes, and then they could just read the messages that were coming in after that. So the information they would get from this stuff would be a day behind, but when it came to massive troop movements or the fact that some U-boats were going to rendezvous at a particular location in 5 days' time, that was plenty enough. And so it really changed everything, changed the tide of the war. The fact that there's a good movie about this whole Bletchley Park thing. It's not a great movie, but it's an okay movie, with Benedict Cumberbatch playing Alan Turing, who was the mathematician that was one of the principal architects of the scheme to break the codes. Anyway, what was it called? The Enigma game, or the Enigma? Well, anyway, I'll remember it before class tomorrow, and I'll tell you that. What I've been holding in my hand here is a 3D printed object that I made several years ago to allow people to play with a sort of toy example. The kind of cryptography that the folks I was just talking about were doing is pretty advanced. But the first time somebody used the idea of hidden writing was in ancient Rome, and it's known as the Caesar cipher. I believe the Romans were about to fight the Phoenicians, and whoever the current Caesar was came up with this idea for being able to send hidden messages to his generals. The idea was you had a massive Phoenician army, right? And you had smaller forces on the Roman side, but they were separated. And you had different generals in charge of each unit. If you could attack the Phoenicians all at once from different directions, they were toast. So that's what they did. They used runners to send hidden messages to the Phoenicians. I don't know if you can imagine this in your mind's eye. Imagine this is a time when, you know, there was no firearms. It was all swords and spears and things. If you were the guy carrying a message and the Phoenicians happened to catch you, they would torture you. I mean, it would be ugly. And then they'd kill you anyway, most likely. So the guy who's running could not know what the message was because he would give it up for sure if he was captured. So they came up with a scheme for hiding the message even from the guy who was carrying it. He had a scrap of paper, maybe he could read, although, you know, back in those days, hardly anybody could. Even in the Roman Empire, which was considered civilization at the time, literacy wasn't a big thing. So anyway, to make a long story short, here's the scheme. They said, if you've got a letter, let's call it X, but I don't mean the letter X. I mean X is well, okay. First, I think we should do this. We're going to work mod 26. Because there's 26 letters in the alphabet. So the basic thing is to assign to each letter a number. So 0 is A, 1 is B, 2 is C, etc. It's a little funky writing an equal sign there, but I think you get what I mean. So what the Caesar shift was this. A message letter X would get turned into X plus 3, but done mod 26. So even in this, you know, old school, I don't know when this was, probably early hundreds AD, they were doing modular arithmetic, although they didn't know it. They just said, move up 3 in the alphabet, right? That's how you could do the encoding. And if you wanted to decode, undoing this is really easy. You just, instead of adding 3, you subtract 3. And you have a little thing to do if you get to the end, which is to say, you know, if you're at like Y and moving up 3 would take you off the end of the alphabet, well, just start back at the beginning. In other words, circulate and make it a modular arithmetic thing. So this, I don't know if the lighting will allow you guys to see this, but this thing is set up so that the top letters I'll think of as the plain text. And do you see how there's a D right under A? I hope you can. A, D. Well, that's the shift, because A is the starting point. B, C, D is going up 3 from there. So A would go to D, B would go to C, etc. So let's pretend we're Caesar and we're going to send this message to our generals. I don't know if this is actually the message the dude sent the very first time with this system, but in all the crypto books, this is the one they use. Attack at dawn. I know this couldn't have been the original message that Caesar sent because it's in English and it's not in Latin, which, you know, clearly he would have written in Latin. But let's figure out what that message would look like after we did some encryption. Well, first off, do you notice that the thing would be perfectly readable if I just wrote it all together? In other words, didn't have the spaces. And that's a smart thing to do if you're trying to do encrypted stuff, because you don't want the lengths of the words to give stuff away. Like, there's a word of length 2. I mean, how many of those are there in the English language? Like 50. 52, I think, is what I remember from my years doing Scrabble. Whoops. So we don't want these spaces. And if they weren't there, if the words were kind of packed together, you'd still be able to read it. You'd still be able to figure out what the message is. So let me start back up at the top, and we'll undo that bit. That is, we'll think of the message string as just a sequence of letters with no spaces in it. This is a little weird because we already know it says attack at dawn, and But, you know, put yourself in the position if you were trying to read that and you didn't have the spaces to clue you in that, you know, that was the end of the word. You'd still know that, there is no English word that ends in aka. You know, that you'd never see that particular sequence, and you'd realize where the split was. All right, so I'm going to look things up on my little ring here as we go. I shouldn't have to look up A because A is D. By the way, in encryption, this is nice that you can do a whole bunch of it at once. All the A's are going to turn into D's. And there's another one. T. What happens to T? T goes to W. So we've got a W there, a W there. Are there any other T's? Yep, there's one. C. What goes on with C? A, B, C. C goes to F. Darn, that's the only one. Well, but you know, I'm almost done already. What must D go? If C goes to F, what does D go to? G, right? I didn't even have to use my... All right, let me check. Yep, D goes to G. K. Yeah, K goes to... That's an N. W. That's all the way at the end of the alphabet. But it's not quite far enough because X, Y, Z. Yeah, you don't have to go around the end on this. And then finally the N. L, M, N, O, P, Q. You can just count on your fingers too. You don't have to use this mechanism I've got here. But sure enough, N goes to Q. So that's what would have been written on a scrap of paper. The runner has no clue what it means. The Phoenicians have no clue what it means. Even if he gets captured, the secret is safe, although that means that one of the generals isn't going to know about attacking at dawn, but they probably would have sent multiple people with the message, hoping that they would be able to get through to their intended recipient. So that's the first use of cryptography in military history, at least as far as we know. There's one other thing I've seen, which is kind of interesting. You take like a leather belt and you write on it, and you have a cylinder, which you can then wrap that belt around, and the diameter of the cylinder determines what letters line up with each other on the belt. So mostly you've written garbage on it, but at some point across the thing, once the belt is wrapped up on the cylinder, you see an actual message. So that's an interesting scheme too, but not as mathematical. Well, I suppose it might be. All right, yeah, this stinks as an encryption scheme. Because what if the secret gets out? The secret is this sort of this notion that we're going to change things by moving up 3. So you could do what this little device implements. You know, if I only had moving by 3, I wouldn't have these rings be movable. But this thing can move by any amount. That's called a shift cipher. I should give you a piece of terminology while we're here. This 3, that's known as the key. If you know about 3, if you know that it's adding 3 to encode, then it'll be subtracting 3 to decode, you basically got the system. So the idea of a general cipher, or a general shift cipher anyway, is to use things besides 3. Of course, you wouldn't want to use 0, but some amount of shift, and it could be 3 or it could be whatever. 26 is bad too, right? It's the same as 0. So the shift cipher is just the obvious generalization of the of Caesar's cipher. X gets mapped to X plus a constant, 126. And there, instead of this one secret that we set for all time, there's lots of different choices. So you could say, you know, to your generals, if you get a message on Tuesday, the shift amount will be 7. And if you get a message on Wednesday, the shift amount will be 9. You know, mix it up. You can even make negative shifts if you want, but it actually is the same thing to shift a large positive number as it is to shift a small negative number. Well, how good is this? How good is this system? You'll find that if you shift by some amount, you'll get equally garbage looking stuff. But there's a problem with natural languages, although this particular phrase doesn't include it. But usually there's certain letters that you see much more often. And I think probably anybody who's watched Wheel of Fortune knows what they are. E's, I mean, it's like 20% of all the letters in English are E's. RSTLN, those consonants they give, those are the most common consonants. I think after E it's A, and you'll notice we've got a lot of A's in this. So if I were trying to decode, that is do some cryptanalysis or cryptology on this thing, I would probably look at it and go, wow, those D's that I see all over the place, there's 4 D's in this message. Those are either E's or A's. So that would give me a sort of framework to get looking at, and then it wouldn't take long, or it wouldn't take many messages. If you had, a real paragraph long message, you'd be able to just count the frequency of the letters, and you would figure out what they encoded to. And you may not get every letter right, but it's amazing how easy it is to read something when the E and the RSTLN are known. As again, you've probably seen on Wheel of Fortune. So the shift cipher sucks because A, it's not that hard to decrypt something that's just a direct substitution like this anyway. But B, there's only 25 possible keys. You can try them all. That's called a key search, or brute force key search. Let me give you an example of how you would do a brute force key search with this encoded message about the attacking at dawn business. So if we had D, W, W, D, F, and I'm not going to finish it. This will be enough to let us figure it out. You can just kind of imagine writing the alphabet around this thing. I'm going to need just a little more space, so let's eliminate the word that says what we're doing. So right before D would be C, B, A, B, C, D, E, F, G, okay. Not so good. Well, we don't have enough yet, but write the alphabet around W. W, X, Y, Z. That's before W. Q, R, S, T, U, V, T, U, V, W. Is that right? So far, so good. Oh, wait, the next one's another W, so we just got this. What have I just done? T, U, V, W, X, Y, Z. All right, look at this last one. G, Z, Z, there is nothing in English that starts like that. F, Y, Y, I don't think so. X, X, well, it might happen, but I can't think of where. C, V, V, not so much. B, U, U, oh. Man, it's already pretty clear that none of these things work except the ATT. So looks like the shift amount was 3. And of course, we already know that's an A, and F, E, D, C. Okay, that's looking like a word. Is this going to be a K? Right, So yeah, you can relatively quickly zero in on a shift cipher. It would be tougher if the shift was something up like, around 17. I'd have to write out more of the alphabet, but in practice you would do this with a machine anyway. Well, not in Roman times, but today we would. All right, so that's not good because the key space is small. So there's only 26 possible amounts, 25 usable amounts of shift. How can we do better? Well, in Mod 26, you can solve linear equations. So if you did this, x goes to mx plus b, Mod 26, all you need to be able to do is solve that. That is, if you've got mx plus b, can you, and you know what m and b are, can you figure out what x is? Then you can clearly encrypt. Can you decrypt? This relies on something important, though. Think about the process of, suppose you know what y is. Y is mx plus b. And you want to find out what x is. Algebraically, that's the process of solving for x. So you would first subtract b. And then you would multiply by 1 over m. The inverse for m, and you get x. Subtracting b we can always do, but can we always find an inverse for m? Not necessarily. Because this has to be done in Mod 26, yeah? So x going to mx plus b is invertible, provided that m is relatively prime to 26. Oops. If that's the case, then you can find an inverse for m, and you can subtract b and multiply by m inverse. So we do need this mapping to be invertible, right? Because, well, if you can't find the inverse, then it means you can't do the decoding. It's not enough to just scramble your message. Somebody else has to be able to unscramble it. So this means, what does this mean? M can't be even, and it can't be 13. Right? So aside from that still leaves a lot of things, doesn't it? All the odd numbers, there'd be 13 of them, minus one of them. So there's 12 different m's. You just say 12 possibilities. And the b, I think you can do everything from 0 to 25. So b has 26 options. So the so-called affine cipher, and that's what this is known as. I should have written that first. Affine cipher has a key space, and the key space is simply the set of all possible keys. You need both of these numbers to provide a key. Well, 12 times 26 seems kind of big. 260 and then another, 52. All right, so that is, wait a minute, I just grabbed a calculator. 26 times 12, 312. So we have 312 different keys. That's better. I mean, by hand, it would be a pain to try to go through all 312 possibilities. It still might be conceivable to do if you had enough time and you had enough messages. You could do a frequency analysis, like I said before, but just brute forcing through 25 things, not so hard. Going through 312 things, a little bit tougher. Until computers came along, of course, in which case, yeah, that wouldn't be much of a challenge either. So the next kind of phase of this Cold War of increasing cryptography and subsequent increasing of cryptology, making codes and breaking codes, was a permutation cipher. So for a permutation cipher, I'm going to do this off camera. Wait, yeah, hold on. That was just sort of silly. I had to write out the entire alphabet, and I knew that was going to take a little bit of time. So here's what the permutation cipher is. You randomly pick a letter and say that'll be where A goes. So that is maybe H. Okay, so A, any H's you see, there'll be A's. Where should B go? I don't care. How about here? C, right there. D, down here. You get the idea. I'm just going to randomly choose positions. So when I get done doing that, I'm not going to finish it, but if I were to completely do that, I've got a huge permutation of the alphabet. How many different permutations do you think there are for 26 letters? I was sort of showing you where I could write the things. So let's think about our choices at each stage in doing that. How many choices did I have for where to write this A? Well, I probably wouldn't want to put it here, but let's count that as an option anyway, because that might really actually be confusing if they think the A can't actually be an A, can it? And then it's, you know, anyway, so it looks like there's 26 options for where A goes, right? Now where did B go? Well, it's got to go somewhere where A didn't go, right? So there's a lot of options still, but not 26 anymore. There's 25. And then the C will have 24 choices, etc. That's 26 factorial, in other words. 26 factorial is a pretty big number. I don't know it offhand, but it's number 4 under the probability menu. It's in scientific notation. It's 4.03 times 10 to the 26 power. So if you have that many keys to search through, because the thing I'm describing here, a permutation of the alphabet, that's the key, you'd be spending quite a long time trying to try all the keys. On the other hand, a permutation cipher like this is not going to be great in terms of cryptology because, again, there's way more E's than anything else. So wherever E gets mapped to, if E ends up being V, well, you're going to see a lot of V's in the message. You're going to see a lot of H's too from the A's. And if you have enough, what do they call that stuff? There's a special name cryptologists use for messages that they've got that they, you know, that can't think of it right now. But anyway, the stock that you're trying to work with, if you've got enough of this encrypted stuff, you can subject it to statistical analysis of how many letters there are. There's also things like, you know, 2-letter pairs. There's certain pairs that happen all the time in English. TH, for instance. There's a lot of THs out there. All right, so while there's a tremendous number of keys in that particular scheme, it's still not really very secure. If you've got some messages to work with, you'll be able to figure out what the different letters are and eventually figure out what exactly the permutation is. So it's still not good. Well, that was state of the art up into the French Revolution. And a man named Vigenère came along and came up with a really, really bad code, a really hard code to do. The Vigenère cipher, I think it's with that sort of accent in it. I might be wrong, but anyway, his cipher, it changes how much the shift is depending on where you are. That is, the shift amount is variable. And that makes it really hard to choose, hard to break, because, you know, sometimes E will get encrypted to F, and sometimes E will get encrypted to G. You know, if the shift amount is changing on you. that was a real advance. But people weren't done. Finally, around this time, somebody realized we can make the shift variable and not have ever have any repeat of whatever scheme we've used to make the shift be variable. That is, this thing led to something called the one-time pad. Now, what is a one-time pad? First off, one time means you're a spy or something, you use this once and then you get rid of it. You're not allowed to use it a second time. Because the second time you use it, they can do what's known as differential cryptanalysis and break both codes. So it can only be used once, and it's a pad. Well, a pad is what Vigenère called it. Well, probably not, because he probably would have had a French word, but anyway. A pad is the sort of thing that the Vigenère cipher used. In the Vigenère cipher, the pad would be some pre-selected bit of text. But in the one-time pad, this thing is random. So it's a random sequence of numbers between 0 and 25. Actually, or in real use, they would write it as letters. So if you just saw a bunch of random-looking letters, long thing. So it would be a whole page of paper just filled with crazy-looking letter sequences like that. Each one tells you how much to shift. So a W would be shift backwards 4. An A would be shift forward. No, actually, an A would be leave it alone. X would, you get the idea. So if you have a thing like that, you can take your message I don't have enough for the whole message, but we can at least attack at. And A gets shifted by W. T gets shifted by A. That one I know. Do you get the idea that you could, this thing that you would write down here, where you variably shift depending on stuff that was randomly generated? It's unbreakable. You'd never have, you'd not be able to use the statistical idea of counting where there's a whole lot of E's, because sometimes E's would be encrypted as one thing, sometimes as another. It relies heavily, though, on this truly being a random thing. And apparently, in World War II, they were using one-time pads for British spies, and they had a bunch of women who were tasked with this seemingly crazy task. They didn't know why they were doing it, but they knew it was part of the war effort. It was a big deal, so they were generating one-time pads. They had a big cage, they call it, for bingo. You crank the thing around and you select a ball out. It's got a letter on it. And then you put the ball back in and you spin it some more and you get another letter. And they did that over and over and over again, writing down these random letters. And that would be what spies could use as their one-time pads. But the ladies, I guess they knew that it was something to do with spycraft and they wanted it to be good. So they kept doing things. They would notice, oh, we just had a cue. Don't use that cue. Throw that back and get another one. And by doing that, by making it, to their mind, seem more random, they actually made it less random. They introduced enough entropy into the one-time pads that they were breakable. Fortunately, it was British code breakers that were, trying to see if there were issues with their encryptions that caught it, but it could have been a major loss. Okay, almost there. We've got two more kinds of ciphers to talk about. And that'll be enough of your intro to crypto for today, I think. The first of those is a polyalphabetic cipher. I guess that's hyphenated. So this is still, this is not one-time pads, although I suppose it could be, but generally with one-time pad you don't care, you just use single characters as thing. When they say polyalphabetic, it means that you sort of have two separate alphabets, or three separate alphabets. I think the best way to think of it is this: you consider your message broken up into groups of so many. Um, well, let's do a particular example. Trialphabetic. Means you break your message up into groups of three. Let's see. We attack at dawn. Okay, and you break it up into groups of three, like this. And we need one more for that group of three, so typically people just would write an extra character there at the end. All right, and then each one of these groups of three can be thought of as a number. You have to think of it as a base 26 number. So this is W times 26 squared plus E times 26 plus A. Where, well, the values of W, E, and A are actually their positions in the alphabet. Although the book would treat A as 1, I would say A should be 0. E is 5. What is W? X, Y, Z? Z is 26. 23? So this is basically a base 26 number. We're thinking of that triple of things as a base 26 number. Well, now you've got things that are, well, they're big numbers, right? How big is that number? What's the biggest a number of this sort could be? 1 times 26 cubed would be the next number bigger than the, although 0 is a possibility too. So, yeah, I guess it's 26 cubed possible values for that number. $17,576. So what we're going to do is work mod, I just said the number, but I don't even need it. Work mod 26 cubed. Now you've got a lot of different keys, and you could do an affine cipher or something else with these triples of numbers, triples of letters. Yeah, that opens up some options. What the Germans did in World War II was adapt a commercial coding machine, which did a 5 alphabetic cipher. So 5 tuples of letters were required before it could encode something. So it apparently was really kind of eerie to type on this machine. It was a typewriter. You would type letters, and after you hit 5 of them, it would go. It would type the next thing. But you know, at first you're getting silence, and then after the 5th letter, it types. Anyway, this machine had a bunch of wheels and settings and stuff, and the German army said, that's pretty good. It was good enough for industrial secret messaging, but we'll put some extra bells and whistles on it. So they had a 5 alphabetic cipher, which was encrypted with a very complicated scheme of, you know, I think they ended up with 5 different drums and rotor settings that they could put on the thing, and then there was some electrical stuff on top of it as well, which apparently didn't do much, but it made it feel more secure. It was broken. It was easily broken. Not easily, I shouldn't say that. It was, with the computing power that they had at the time, it was a big deal to break it. But, you know, this thing has hundreds, maybe millions of times more power in it than the machines that broke the Enigma code. So, I don't know, there's that. Certainly not breakable by hand, but with rudimentary computing power, not too hard to break. Okay, finally we're ready to talk about the DH scheme. Diffie and Hellman are the first people to think about using mathematics to, well, number theory in particular, to develop a coding scheme. That pen is bad. Here, try this one. These two gentlemen were computer scientists, I believe, more so than mathematicians. But what they did was say, you know, you don't have to stop at tri-alphabetic or 5 alphabetic things. You can let arbitrarily long strings of text be represented as a number. It's just a number base 26. So first, rewrite strings as numbers. That's sort of the easy part. The second phase, though, is to use an invertible function in modular arithmetic. And the one that they chose to use is modular exponentiation. So what they had to do first, if you're going to rewrite your strings as numbers, a string might be a whole paragraph worth of text. That's a fairly big number. So they had to choose a p that was relatively large. It needed to be bigger than the biggest number that would come from encoding the strings. So large, but not that crazy large. It depends on how long you want to make the strings. Something with 20 or 30 digits in it would be fine. Then you'd get to have strings of maybe length 12. Yeah, that would be big enough. So a large prime. And modular exponentiation. So what that means is a message x is going to get sent to x raised to some power on a p. Well, we know now that not every E will work for this. Not every E will give us a nice encoding scheme. When is it something that we can in fact invert? It's precisely when E is something that's invertible in U of P. So what you need is this, that the GCD of E and U of P, that's P minus 1. These guys have to be prime to one another. So the GCD of E and P minus 1 is 1. And once you pick that E, basically what this does is make a crazy scramble of the number that you got from rewriting your string. I'm using this word string, I hope, in a way that people have heard before. A string of letters, a snippet of text. Anyway, the string gets represented as a number, then we raise it to the E power, and provided we've got this, there's a way to decode. You see, if you raise x to the E power to the E inverse power, whatever E inverse is, those things collapse and you just get x. And because of this condition that we choose E so that it's relatively prime to the group that's in consideration there when you're working in the exponents, it does have an inverse. So that has to be computed at first, but it's not hard to do, and you've got a way to decode. All right, I think that is where we'll call it for today. This is the scheme that we'll do in toy versions anyway in tomorrow's worksheet. So I want to get this thing posted for you as soon as I can.